Hi everyone, in this video we're going to take a little bit deeper dive into just the p-value. So the p-value, again, just to remind you from the last video, we're going to assume the null hypothesis is true. The p-value will be the probability of getting the value of the observed statistic or more extreme. So if you want to put this in terms of an example for yourself, remember what we did here with Buzz and Doris. So this line here says assume Buzz is just guessing, right? So assuming Buzz is just guessing, the p-value is the probability. So you can still use the word chance there for yourself if you want, just while you're thinking about probability. So p-value is the chance, the probability, whatever, of Buzz and Doris getting 15 out of 16 or more extreme. So we assume they're just guessing. Under that assumption, look, we're just in our minds, we're saying they are just guessing, they are just guessing. We look at the probability of them getting 15 out of 16, something so good, right, or more extreme. We say, nah, doesn't seem right, and so we throw out our null hypothesis. We say, hit the road, null hypothesis. So how do we actually get this? So I mentioned it just briefly last time, we're counting dots, but we have to be a little careful here because depending on the alternative hypothesis, we have to count the dots in a certain way. So let's go back up to the Buzz and Doris example. All right, so if we go back up here, let me get rid of some of this so we have some room. Okay. So there are three situations we need to be thinking about. The three situations are your alternative hypothesis has a greater than symbol, has a less than symbol, has a not equal to symbol. In this example, we were interested in greater than. We wanted to know if the dolphins were communicating, and to us that meant they should do better than 50%. So how did we do this? To do the p-value, we found 15. We went, okay, 15's right here. We found 15, and we counted the dots at 15 and to the right, greater than, to the right. Right? So that's how we do greater than. You find your statistic, count all the dots there and to the right. Well, what's another option? Another option is, let's do less than. So, okay, what if, let's just change it up a little bit. What if Buzz and Doris only got 2 out of 16 right? We would find 2. We would drop a little line down here for ourselves, and we would count all the dots at 2 or to the left, because less than means go left on the graph. All right? So we would it's still more extreme because it's further from the middle, but it's to the left now. So less than, we go left. Greater than, we go right. Okay, so then what about not equal to? Well, remember what not equal to meant. Not equal to meant, I don't know which one it should be. I just am thinking it's not equal to. So it could be bigger or it could be smaller. So it's a little tough for us to do that. We have a computer do this for us. But what we do in essence is we say, okay, for not equal to, here's what I'm going to do. I'm going to find my statistic. Let's assume it's the 15 out of 16. I'm going to draw the line. I'm going to count all the dots there and to the right. Okay, this seems familiar, right? We already did this with the greater than. But wait, not equal to includes greater than and less than. So I have got to find a statistic over on the left that's about as extreme as 15. So I got to wrap myself back around to the left-hand side. Find a statistic that's about as extreme as 15 and count the dots there and to the left. I'm trying to take all the possible evidence that could support not equal to. What does that mean? That means I've got to take everything big and everything small that's extreme, that's at that same level of being extreme. So The not equal to, they call it two-sided. So let me just write that down for you, two-sided. Because I want to look at the probability of this happening, I need to look at the probability of big things happening, just as big and extreme, and just as small and extreme. I want it all because all of that supports my alternative. Any statistic that pops into the simulation that's as extreme on either end, big or small, I want that to support my alternative. Okay, so that's an important thing. We'll talk about this two-sidedness and the extra dots that you probably get and what that means for your conclusions. We'll talk about that later. Okay, so those are your three options. Bigger than, less than, not equal to. And that's how we count them, okay? So how do we do it using the simulator? So I'm on the Rossmann-Chance applet collection now, and all we have to do is go to the one proportion inference. We just do what we have been doing, right? We create our chance model. So for Buzz and Doris, it was 0.5, 16, and we can do 1,000. We still hit draw samples, get our nice little picture, and all we have to do is go into this box here. So what we have to do is, and this is where it gets a little tricky, number of heads is currently selected, and that was 15 heads they got. So the way that you enter this number, its form has to match this form. And all you got to do is look at how these numbers look to kind of make sure. We hit count, and look at that. It finds 15, draws a line, and it will count everything there and to the right. And we get 0 out of 1,000. There you go. If, on the other hand, just to kind of play around, we were like, well, what about 2? Plug 2 in, hit count. But what did we do wrong? If we're looking at 2, that means we're probably looking at evidence of less than. So we have to click this button, and it becomes less than. 6 out of 1,000, that's our p-value. Well, what if we had started this and we didn't know? Not equal to is our alternative. You go right down here and you hit two-sided. Boom. It'll take 2, that's your statistic, and it'll find for you a statistic all the way on the other end that's as extreme, it's just bigger instead of smaller. And it'll count all the dots to the right of 14, including it, plus all the dots at 2 and to the left. And you can actually see that it does that, which is pretty neat. This was coming from the 2 and left. This 0 is coming from the 14 and right. So there we go. That's it. Okay, so now we know how to get a p-value by counting dots, looking at the proportion, or by using the simulation. So what do we do with it? We get a number, so what? So we've already talked about this a little bit. A small p-value, smaller the p-value, right? That means the probability of us getting what we got was small, really small. So smaller it goes, the smaller the probability, the chance that we could get something so extreme. So the smaller that chance is, the more I'm thinking, no, I don't think it's the null. So what does that mean? Smaller the p-value, the more support we have of the alternative. Okay. Big p-value, the bigger the p-value means the less evidence we have for the alternative, right? So a p-value that's bigger says the probability of you getting your statistic, assuming the null, well, it's high enough where you're like, okay, that could happen. So then you say the null hypothesis is plausible. There you go. Small p-value, strong. Big p-value, weak, or you could say null hypothesis is plausible. So if we have a small p-value, I'm going to say I support the alternative. If I have a big p-value, I'm going to say, null hypothesis is plausible. So to make this more concrete, because I promised you concreteness, we have this little number line set up. And what we're going to stick to in this class, although there will be, we will spend a little time talking about these cutoff points because it is an important idea. What we're going to do in this class is we're going to have this general setup here where if your p-value is in here, so if you're in this purple, we are going to say you've got very strong support. So if the probability of you getting your result, assuming the null hypothesis, is between 0 to 1%, well, that's not very likely. Let's throw out the null. That's what that first one says. Okay, what about the next one? If you're in here, this one's taking me longer. If you're in here, 1 to 5%, we'll say, okay, that's small. We've got some good support for the alternative. It's not as good as the purple, 0 to 1%, but it's still pretty good. If you get bigger than that, so if you get any bigger than that, so that's, you're leaving 0.5 all the way to 0.1 and then bigger, we're going to say, you know, that's just not quite enough for me to throw out the null hypothesis. If you give me a p-value that's bigger than 0.5, so bigger than 5% probability, then I'm going to say, no, I don't really think I can throw out the null. I think I'm going to have to say the null's plausible. So what you might think now is, you know, why? Why are these the cutoffs? And that's a more complicated conversation, and you know, we'll get into it, and you'll see that sometimes the cutoffs can change. And we'll talk about when that happens and how we make sure we know where the cutoff is before we say plausible null or throw out the null, let's go for the alternative.